All right, at this time, I'd like to introduce Mr. Richard Pryce, our keynote speaker. Mr. Pryce is the current president of the Florida Surveying and Mapping Society. His career spans over 52 years and includes expertise in surveying and mapping, GIS, and remote sensing. He started his career in surveying and mapping in 1972 and became a licensed surveyor in the state of Florida in 1983. His first experience with GIS was InfoCAD, developed in Miami in 92 through 96. He tried out the GRASS software by the Army Corps of Engineers from 92 to 94, but found it to be too complicated. He was introduced to Esri ArcInfo 7.1 in 96, a Unix-based software with 35,000 command lines, and helped develop the GIS parcel map for Broward County Property Appraiser between 1996 and 2004 as his first big GIS project. He has since continued his experience with Esri to the current and last version of ArcGIS ArcMap 10.8.2 through today, and just starting to get into ArcGIS Pro. Over the last 4 decades, he has developed and presented multiple seminars for surveyors and GIS user groups and completed dozens of survey and GIS infrastructure projects for several cities. His latest and largest project ever was just completed in June of 2024, accurately mapping the entire water system for the city of Fort Lauderdale in ArcGIS in 18 months. This included over 766 miles of water mains, 4 inches and larger, 23,000 valves, 7,300 hydrants, 271 control valves, 138 wells, and 64,000 water meters. He had the entire city and water service area covering 45,432 acres, flown with 2-inch pixel aerials and dense LiDAR with 120 to 150 points per square meter on the ground. And every roadway with water mains, that's 823 miles, was driven with mobile LiDAR. So please let me introduce you to Mr. Richard Pryce.
Thank you. It's nice to be here. It's nice to be invited. First time I've been over to GeoFlo. I'm happy to present for you. Basically, my presentation is on projects I've done over the last 5 decades. These are unique projects that actually took some unique thinking to get through, including the last project you mentioned, which I'll have in here. So without further ado, thinking outside the box. I mean, we all go through this periodically, come up against a problem or two, and it doesn't meet the criteria that we're used to, and sometimes we have to get along with other people, get their ideas how to do this, and you have to think about it. It really taxes your brain. Well, these are the projects I really like. These are the things that keep me going, keep me interested. As you can see, over the years, I started off back in '72 with transit and tape. Did my first calculations with slide rule. And when we obviously went forward, we got into a mechanical calculator, which you push the buttons in, pull the lever, and it does your calculations for you. And we went on to '75 when HP came out with their calculators. And the 9815, which was HP's next version, went into buying HP 41C, which I bought in 1982, 2 months before I took my test. I still have that. It still works. So you see the quality HP 9816 when they went to the diode, the green screen diode, and then further on from that. And of course, the reason why we go with HP is because they were the first ones that came out with a square root button on the calculator. In case you never had to use that, it was a very important feature back then. These are some of the things I've been through. Got 52 years of surveying, 28 years with Esri products, conversions between AutoCAD and Esri products. Got back into laser scanning. I saw it back in 2004. Actually started doing laser scanning back in 2006. We were one of the first 2 firms in Florida that had it. And my current thing is I'm giving back to my profession and the people like you that from my experiences with GIS. These are the different programs I've gone through over my career. Original HP programs for surveying. First got into GIS with InfoCAD, was with a company out of Miami. I went into GRASS because I heard that was a better program. I saw GIS almost immediately when I was introduced to it as the thing that's going to happen in the future. Now, I got into Esri back in 1996 doing the parcel maps for Broward County Property Appraiser. That's where I really started to learn it. I mean, we had 35,000 command lines. Esri was not a perfect program, but if you didn't type it in right, it never worked. So then we went into, so on the survey side, so AutoCAD and AutoCAD map. I did remote sensing with a firm for a while. We did Erdos Imagine, where we did classifications of sugarcane fields around Okeechobee. And then I got into laser scanning, Global Mapper, Google Earth Pro back in 2004 when it first came out. It was produced by a company called Keystone, I think, something like that. Anyways, when I first learned that, and I've developed all kinds of ways of using Google Earth Pro with GIS as well. I have a problem with my throat. I had an operation on my vocal cord, so if you can't hear me, just tell me and I'll try to pick it up. The Geomatics program in IFAS we went from a survey program to a geomatics program. And what we found out over my conversation with the IFAS people was it came about in 1997. Dr. Dave Gibson back then took a trip to Canada, where he went a surveying program seminar up there, found out about the word geomatics. Geomatics is, he brought it back as we need to broaden the scope of surveying and mapping and include geomatics. So that, because we really do utilize everything that you guys use, remote sensing, photogrammetry, anything revolved around Earth mapping. So surveying and GIS are really linked at the hip. Now, you guys probably need our accurate maps for your work, maybe not, but ever since I've been into GIS, I've championed GIS, doing GIS products for multiple cities and linking engineering, surveying, and GIS together. Aerial LiDAR. How many people use aerial LiDAR? Okay. Do you really understand it, what it does for you? It was patented back in 1969. You know how far away that was. I mean, the digital cameras back then and the laser scanners were separated. Nowadays, they're combined together so that when the plane goes up, you can take the digital photos as well as the LiDAR at the same time, so they match almost perfectly. If you don't know, normal LiDAR flown from a plane, it's the sensor is sweeping the ground at 90 degrees to the plane, sending out pulses, 2,000 pulses per second, or 2 million pulses per second. And what that does is it gives you multiple returns, because as that pulse of light comes down, it widens out. Whatever it hits first of that light will be the first return it gets back. Those returns can be classified just like GIS. And these are the different classifications that you can put into there. Most of the time on surveying and mapping, I'm only interested in the water, the ground, the vegetation. So we classify it that way. But you can have up to 225 classifications within the LiDAR. I deal with LiDAR a lot. Most of Florida and around the United States, USGS program is the 3-depth program, if you've heard about it. This is the density of the points. This is part of the runway for Fort Lauderdale International Airport. This is recent, I think it was 2018 LiDAR from USGS. in 3 years ago, FDOT did a project where they're testing more denser LiDAR, same area with 90 points per square meter on the ground. And what I look at when I hire somebody to do the LiDAR for me, I want them to give me the densest LiDAR possible so that I can see more information on the ground, collect the information, use it for surveying and mapping, use it for GIS purposes. And my latest project, we had 150 to 160 points per square meter. So you can see the information that you're gathering. Of course, you're getting up to multiple gigabytes of data. So you have to look at, your tiles within the data as well. My first really big project with GIS was the Florida Gas Transmission Polaris project back in 1999. We did 827 miles of natural gas pipelines. Those red areas are the areas we did. That was class 3 and 4 natural gas pipelines. So the only reason we got the job from the Texas firms that normally do this, because we did surveying and mapping, but we also did GIS. This was the first GIS Florida Gas had. They had they had a GIS system, but all their mains were plus or minus 400 feet off, basically just for viewing purposes. They wanted it down to 2 to 3 feet accuracy across these areas. These are the areas that go through heavily populated areas. They needed to know where those pipelines were. So what we did, we had 2 main crews. We connect directly to the main with a device. I'll show you what it is. And we'd send a DC current down the main. The man would walk the main just like you see the underground people nowadays. He would mark it. Had a guy with a backpack GPS unit back in 1999, and he would locate the points every 200 feet along the main. We also had to do classification of all the structures within 1,200 feet of the pipeline. The way we did that was we hired a aerial firm to fly the route. We gave them survey control to keep it accurate, and they flew the route. And then they did planimetrics on every building within that 1,200-foot corridor. 1,200 feet, that magic number was because that's what they called the burn area. In case they had a leak in the pipe that exploded. So some of these pipes are 36, 48 inch in diameter, under 1 million pounds of pressure underneath the ground. And it would be very difficult to stop it if it started. So this was during the area where they needed the corrosion people in Florida Gas needed to put it into a GIS format. And that's what we did for them. Like I said, we had to classify, we had to go through some very secure areas, get clearance for that. It's the type of units we had. We were the first ones to tie our GPS units into the internet. So I had 6 crews going around the state, 41 different counties. They would collect the data during the day. They would upload it to the internet at night. We would download it at the office and start working on the data. Due to the size of the project, we couldn't use state plane coordinates because it went through three different areas. So we ended up doing everything in meters and using the UTM. So there was only 2 separate coordinate systems. In the end, we did the database. They had 30 years. We had over 900 as-built we had to tie into this, and it was very extensive. Unique project that I did. These are some of the thinking outside the box. City of Hollywood had a 2-mile stretch. They were going to classify the tall buildings in the area. They needed to know every roof deck that was above 120 feet above the ground, not above sea level, but above the ground. This is a 3D image of the area. I took the LiDAR that was available at the time. I showed the city what we were going to do because I needed to know the accuracy they wanted. Used it, what their accuracy was plus or minus half a foot. Now, this was perfect for that. This was the existing LiDAR. I took the property appraiser data to get the parcels so I can understand, I could get the ownership and the address of the different parcels. Use the GIS data for that. Identifying, basically took a road trip out there, identified the parcels I needed, and got the information I needed from the property appraiser. Then I took the LiDAR, I did a profile view of the 2-mile stretch. Pushed it together, and you probably can't see it, but there's elevations on the side in NAVD 88. I was able to identify, used elevation 120 feet above the NAVD 88, and was able to identify which buildings I needed to concentrate on. So without even doing field work, which normally would have taken us probably 2 months of going out there, going to the top of the building, setting up survey instruments, this was something that really worked for them. What they needed was the roof deck done. So I used Google Earth Street View and Google Earth 3D in order to determine where the roof deck was. Oops. I took a 30-foot swath of the LiDAR across the building. And then I did profile views. Now I can see the roof deck. I can get the elevation of the roof deck. And get the elevation of the streets around the site and the average elevation of the site. So basically, I did the whole job with just LiDAR and GIS in a week. So I took something that was going to take us roughly a month, maybe 2 months, and turned it into a week. This is Margaritaville, and which was one of the buildings down on Hollywood Beach. Same situation. So I had about 16 different buildings we ended up checking, and this is the way we did it. Going back to my surveying and laser scanning, had a project for Broward County Parks, Tradewinds Park. I had 215 acre site. They needed surveyed in 60 days. They needed a topographic survey of it. Now they want elevations every 50-foot grid, so they can do their planning. Well, you can see the site is pretty well tree covered on at least half of it, maybe 3/4 of it was tree covered, dense tree cover. It used to be a farm that was laid to rest, donated to the county. So I suggested I asked them what their accuracy standards were. So they need the accuracy of roughly a half a foot of accuracy in the topo, in the treed areas. I said, well, I can do it with LiDAR. So I had the whole site flown with at 1,500 foot and got 60 points per square meter on the ground. I needed it dense. That's why we flew it as low as we could in the airspace. Why isn't this? Oh, no. Oh, there we go. So this couple of slides to show you what the elevations or the LiDAR that we collected and how dense it was. So you can see what we're grabbing there. So I'm going to give you an example of how we got the surface. So here's the tree covered south half of the site. Here's the LiDAR data, which I had classified for ground ground and water. In this case, anything that's vegetation or buildings was not classified because I really didn't need it. So this is what it looks like as soon as you just go down to the ground classification level. This is just the same thing that they're using down in the Yucatan to look for the Mayan, different Mayan cities that have been lost. Same process. So, like I showed you before, once you classify something in LiDAR, you can separate that out. The last return in a LiDAR is normally the ground because it's the last thing it hits. But you have to look at. So you're looking at. So we go from this to this. Then you can do your contours. You can do your elevations, but you have to, as a surveyor, I have to go out there and check, make sure I'm right. So we set targets along all the hard surfaces. The elevations along the hard surfaces came within 1/10 of a foot with the LiDAR. So I'm figuring, okay, now I have to go out there and check the woods. So the crew went out there, checked the wooded areas, went out there, and they were all roughly within a half a foot accuracy in the wooded area. So we met the goal. We did it within 60-day process. Just going to show you a little close up here. So you get down to the ground level. These are the burns and low areas that were underneath the tree cover. This is the number of returns on that. So the different colors there. I think there was 8 to 10 different returns we were getting. Once you classify it, if you look at the green area down the bottom, that's the classified ground. So you can see what it's doing. If you look just at the ground level, the line work is the average ground level within that swath that I took. These were like a 2-foot wide swath. That's how we get the ground level, and then we produce the survey from that. That's where we're thinking out of the box. And the elevations, we had to differentiate those. So the ground elevations with the instruments were the blue area. The spot elevations inside the wooded areas, we put a different symbol in there for. That's how we did it. Separate it out. 2016, we were asked to do the stormwater project for the city of Fort Lauderdale. So from 2016 to now, I went through the stormwater project, then we did the sanitary system in there, and then we just finished the water system. They had 25,000 features. They needed at least 5,000 of them to model the stormwater system. Again, I asked them what their accuracy was. They said 0.2 of a foot for a stormwater, which was fine for modeling purposes. I said, well, this is perfect. So we talked them into flying the entire city with LiDAR back in 2016. Again, I used the process. I needed to get at minimum 60 points per square meter on the ground. Because one of the things they wanted to be able to see the seawalls. They have 125 miles of canals in Fort Lauderdale. Because they're looking at, sea level change. They were looking at putting a process of defining how high the seawalls needed to be. Everybody hear me? So we did a GPS network around the outside. We decided that there were specific areas within the city that they needed to be as accurate as possible. So we densified the PIDs for the aerial company. These are the type of things we use for PIDs. Went around, got elevations on those, flew the whole city, did a statistical analysis on not only the control, to prove what we were getting. So on the vertical control, on the control itself, at 99%, we had 1,500. In the second area, we had 1,600. So we basically met when it was needed by doing that. We not only checked that, but I wanted to check the rest of the city to make sure we got what we wanted so we could make this more useful. So I did over 7,000 cross sections of roadways that we could easily see. And we did multiple surveys across the city that we already had elevations. We checked those. All of those areas checked within that 1,500 tolerance. So now we have a great data set of LiDAR points across the entire city, 25,000 acres at the time. So you can see the level of detail this LiDAR gives you when you get there. We did a 2-foot grid digital elevation model of the entire city for the stormwater master plan from this data. You can see this data picked up, the sidewalks, the curb cuts, the medians. So we were able to get very good contours across the whole city, which they use for their stormwater master plan to cut it out and put it into basins. This is going into why we got one of the other reasons we used it was to look at seawalls. So not only did we fly it with LiDAR, but we flew it with 2-inch pixel aerials. So we could overlay the LiDAR. And we could identify the city-owned seawalls so that we could get the elevations up. Now, remember, this is still within the 1500s tolerance, so, but it met the standards they needed to for their details of what they were going to do for zoning classification. And that's the 2-foot grid digital elevation model. Now we get into the stormwater part of this. Okay, the other reason was now we want to collect all the stormwater data. Okay, so now that we got the LiDAR and the aerials, we can just look at it and we can pick, because we had plus or minus half a foot elevation in horizontal, 1500s in vertical. So now we can collect all the data we want, rim, position, X, Y, and Z of the structures themselves. We can see them. Most of this was done with on the computer, wasn't field work for this part of it. So we got the X, Y, and Z. The density really surprised me because we had problems with Fort Lauderdale International. We couldn't get out there. They kept on delaying us and delaying us. We finally said, let's do it after midnight. And they agreed to that. They had the entire city flown with LiDAR, this dense area LiDAR after midnight. This turned out to be a real plus and something you should think about if you're going to do a whole city, because there was no traffic on the road. So I got clean streets almost across the entire city level. But the density was such that it was actually penetrating the structures. Now, is that the bottom of the structure? I don't know. I thought it was unique that it was actually penetrating the structures. On top of that, we're collecting now, we have to send the crew out to collect what's inside the structure. We got to get the condition, the location. We already had the rim and invert, or rim. And now we have the pipe size, material, the shape, the weirs, baffles, conflicts, and they wanted pictures. All right, Esri has their own field product to go out there and do this, but what we ended up doing was finding the Trimble TerraFlex was a better fit for us. Worked out perfectly. Once we had the geodatabase set up, we could export that out and export it and import it directly into Trimble TerraFlex, create the form right there, the information we need, and they could go out there on their phone or a data collection device, just fill in the form, open up the structure, fill in the form, take the picture right there. We got all the data using this. This is the first time this has been used for a project like this. We helped to prove out that Trimble TerraFlex is a really good product for working with GIS data. Then once it's done, as soon as it's done in the field, you tell it you're done, pick an area, you tell them that the area is done, it goes up to the cloud, we can download it in the office and import it directly back into ArcGIS. On the LiDAR side, the city really wanted us to cut the cost. They wanted us to use the original 2007 LiDAR from FD, Florida Department of Emergency Management. I already tested that across 2 counties. I knew it was bad data, it would not get a consistent elevation. So I went ahead and made the analysis of it for the city so they could see. The south end of the city, I took 1,000 foot of roadways. And at the south end of the city, the 2007 LiDAR was 4/10 below the new LiDAR. In the north end of the city, it was above, 2/10 above. So we were proving that the LiDAR from 2007 was tilted. So that's the reason why we did that. I got into laser scanning in 2006. I saw that as the next big thing. And basically, the way I look at it is basically looking for treasure that you didn't know was there. Why I have the treasure map up there. Back then, you had to sit there and wait for these instruments to spin. If you wanted a dense LiDAR, they would be doing their work and you'd be sitting there for a half an hour to 45 minutes, depends on the density. This is what a crew looks like when they're sitting there waiting for the scanner to finish. I also had mosaic pictures, rudimentary pictures that you could get your color to overlay the LiDAR. The problem was it was a mosaic, and if the person moved, you end up with somebody like this, standing beside himself there. So, okay, like I said, we were one of 2 firms back in, this is 2009. that had laser scanning devices. We worked, this was the collapse of the garage at the Miami-Dade College back then. 4 people died during this. So we got on board with the insurance company called us. We got recommended because he had a laser scan. They wanted everything scanned on the site. That's what it looked like before the collapse. Basically, that crane you see there actually, go over here. That crane was working in this area. It actually bumped this column right here. So it bumped it, nothing happened. OSHA was brought out to the site. They spent a couple of days with that, looking at it. They said it was fine. Everybody went back to work, and the following day after OSHA was there, it collapsed. So shows you their reports are not necessarily perfect. Because of the police operation around it, we had to work at night there. Laser scanning is perfect for that. You don't need light, you just need light to figure out where you are. So we worked there for a solid month. As they moved debris, we scanned it. The insurance company wanted it. That's what it looked like after the collapse. These are the types of things the insurance company, when they wanted the footers scanned, all the different footers that were exposed. Because they wanted to see figure out what reason was that actually collapsed. Because they didn't figure that the crane would have been the real reason. They'd actually pushed the issue that would have happened eventually. And luckily they did, because there was going to be classrooms on the bottom floor. Actually, the day before it collapsed, they set up an OSHA meeting with all the subs that was going to be on the first floor. So luckily it collapsed when it did. Otherwise, it would have had a much more bigger people lose their lives. So these are the types of scans we did. You can see the density because those are only this big. So this is the one that actually created the issue. The scans actually helped to prove it. But this is the level of detail that the insurance companies were wanting from us. And it was rapid fire because they wanted us to scan tonight and they wanted us to get the details the next day. I mean, we did so many that in some cases I had to actually draw it by hand in order to get it to them. I couldn't get it from the scanner quick enough. I also had us afterwards, after they cleaned up the site, they wanted to check the plumbness of the walls, the elevator shafts. And that job right there actually paid for my scanner. So it was very helpful. We do a lot of work on the infrastructure project. We do a lot of work with Hazen and Sawyer, if you don't know who they are. We do plants. We do a lot of interior where we're scanning the pipes and the plants, entire plants, creating 3D models for them. There was several of these deep well injection sites that we've done. I want details of them. These are the ones that Fort Lauderdale, city of Fort Lauderdale has for their system. And they wanted it in 3D. They wanted 3D models of these. So one good thing about laser scanning is it'll actually pick up the wording on the side of the pipe. So we can actually get the pipe itself. If you use AutoCAD Civil 3D or Stormwater, it has the pipes already in there. So once you get the scan of the pipe, you can identify and put the exact pipe in your 3D model. So we've done a number of these. We've done a lot of historical data. City Place in West Palm Beach has some very really nice historical buildings there. So we did that for the people to help not only to identify them, map them out, collect the data so that it's, they have it for future in case anything happens to these buildings. But you can see the level of detail. That's a laser scan, believe it or not. And what happened on this particular job, we had an anomaly that happened to our laser scanner. We couldn't figure it out. I don't know if you can see that, but there's a dome around the setup of one of scanner positions. I looked at that from several different angles just to be aware of what it was, because I couldn't figure it out. Here's the intensity level on it. Then I did a cross section of it just to make sure it was there. I wasn't seeing things. I got a hold of Leica. I got a hold of several people that have laser scans. Nobody could figure out what this phenomenon was. So finally, one of the people at Leica that trained me, I called him up just by chance, and he started laughing. He says, was there any landscape operation in there? I said, I don't know. So I checked with the fire chief. There was people out there with landscape blowing things. This is dust on the lens of the laser. That's what it turned out to be. Like I said, we do a lot of infrastructure. We do a lot of lift stations, several of them being 2 or 3 story lift stations where half of the lift station is below ground. And they're going to rehab the lift station. So we scan both the inside and out using Leica Cyclone software for the scanner. This is what it normally looks like, but I've been using it so long, I've tested different ways of viewing the data. I've tested different densities of the data. You get denser data by making the laser scanner go slower and collect the data. So I collect very dense data. That way I can turn the building invisible. I can see inside the building itself from any angle, from any position on the building. If you're looking straight down on it, you can see the walls, inside walls, the equipment. You can zoom into the structure and get the equipment. And every once in a while, you have visitors that show up. He surprised me. I didn't even know he was there until he picked him up in the scanner. Here's another project for this was for Hazen Sawyer. That's Fisher Island, and across that's Fisher Island. That's Miami Beach. What's happening was they were going to deepen Government Cut there, which is where all the main ships come through. And there was a 48-inch force main going from Fisher Island to Miami Beach. They're going to deepen it by another at least 10 to 15 feet, the Army Corps of Engineers. So they had to replace the force main that had been in there for almost 30 years with a new force main. So they had to get it, they were going to tunnel it across. What happened was Miami Beach didn't want them to dig a shaft on Miami Beach, which is a very popular area of Miami Beach, for construction purposes. That's 2 shafts. That shaft is 22 inches, 22 feet diameter. There's one out in the water that's 13 feet diameter. They're 90 feet deep. They were going to put a tunneling machine down on Fisher Island, dig a 10-foot diameter tunnel from that structure to that structure. And then a third one when they got permission from Miami Beach to get crossover and get that. So they were putting in a 6-inch diameter force main, new one. What they needed to know was the exact center of the bottom of each shaft and a bearing and a distance between them so they could plan their tunneling operation. Now, they're on the surface. As a surveyor, I can collect state plane coordinates on anything I'm on the surface. Now I need to get the coordinates down to the center of the bottom of the shaft so that I can calculate the bearing and distance to the other shaft. Now, if any of you are claustrophobic, this is not nice to work in. This was in July. So my guys were very good. They sweated their butts off down at the bottom of that shaft, but I figured the only way to do this properly is to laser scan not only the inside of the shaft, but the bottom and the top of the shaft. I could coordinate the top, set targets on the top, go down the bottom, set the instrument, the laser scanner up, scan, and I could triangulate the position of the scanner at the base. That's how we figured to do it, and it worked out perfectly to do this. So we had to get the construction people to set up mount these things on the side of the top of the shaft so we can put laser scanning targets on. That's what they look like. And 10 feet from the bottom, we set up 4 more or 6 more to triangulate as well. So we could coordinate the whole inside of that shaft, both shafts. And we end up with a complete scan of the entire both shafts that were out there. This is what the targets look like in the laser scanning. So it's critical for us to calculate. We collected the point where we're putting the target up at the top. So we had to manipulate that. So I need to get that position. So I need to see it in the laser scan to make sure it was calculating the correct position as well. That's what it looks like from the bottom, looking up at the targets. This is the one out in the water. Kept on leaking, so they ended up putting a solid container down at the bottom so it stopped leaking because we couldn't do the work. So you're looking at, and our scanner projects out 300 meters, so we were able to, I thought this was a pretty unique view of the shaft out in the water and the buildings around it. And this is the actual above ground survey data that we did. Collect the information. I've done a lot of unique work with LiDAR. People know what I do. They call me, they ask if it can be done or not. So if you went into a unique something project that you're not sure what you could use on it to get, you can call me. All right, this is a wetland preserve area in West Palm Beach. This area, along with the 15,000 acres around it that you see that's undeveloped north and south of this site, was actually set aside by Henry Flagler back when he was building the railroad. This was, he wanted a pristine area of the Everglades where he could collect the water and the city could use it. So that's where this site came from. Now, the city of West Palm Beach was having a problem with South Florida Water Management District. They felt that they were not keeping this water clean enough in this area because they protect it. They don't allow boats. You only go in here with canoes, things like that. The police actually patrol the outside of it to make sure. So, and they have cameras set up around the edge. Anyways, what they wanted to prove was that the water was flowing correctly. So they wanted a surface of the ground in this area. Where you can see it's mostly wetland. So they had done something previously, like 15 years before we did this, and they wanted something more accurate. So again, we set targets around the site. We flew with dense area LiDAR to 60 points per square meter. We only went 1,400 feet above it, so it could penetrate the trees, the mass. And I needed to check the information as well. So these are targets we set over. We had a lot of wildlife around there. And we're checking into the tide tables from South Florida Water Management District as we were doing the work. These are the type of where we were, the boats we used to get out there. Couldn't use a motorboat, so we had to use our, rowing and electric motors. We went across and did topo across the fields just to check the LiDAR data. But the LiDAR does not penetrate the water. The water blocks it, absorbs the light. Unless you're using a green LiDAR unit, which is topography LiDAR, it does not penetrate. So how am I going to get? So I had guys out there getting depths of the water. Luckily, the water was fairly consistent. The ground underneath the water was fairly consistent. So we got test sites with boats and with airboats that the police use for the area. And we're able to collect data under the water. And in the open water areas, we used our robotic boat to collect those. These are the guys setting the targets out in the wet areas. We would pick the dry time before the water table came up. Several of these targets, even though we had them perfectly above ground, we picked it perfectly so that the target was still above water even when it got inundated. I had to wait like 3 months before it could be flown. When we came back with the airboats checking other things, we found alligators resting on top of the targets across the site. Some of the targets we had to move and replace because the heaviness of the alligator was actually bending the targets. Anyways, we got the whole thing flown, the base, the ground level classified so that I could extract it. The thing is, I had to build two separate surfaces in order to get a surface of the entire ground. I had to take the water elevations that we got, take the LiDAR, cut out the water of the LiDAR, then take the area and build a surface underwater and build a surface from the ground points that we were able to prove that. So then I had to merge the two surfaces together in order to get a complete ground across the whole site. This took us pretty much 8 months to do this. But the level of detail we collected was, it even amazed me once I got done. And they were able to use that in a court case against South Florida Water Management District. So I guess they mended their ways there. Okay, the last one I want to go over is the project I just finished, which is the Fort Lauderdale water system. It was not only Fort Lauderdale water system, it was a water service area. They had about 45,000 acres, plus transmission lines going across other cities. So there was 63 land sections in there, section, township, and ranges in there. And these are before, there was 750 miles in their existing GIS. We ended up with 769 miles. I don't remember, over 7,000 fire hydrants, 22,000 valves, if I remember right. And there ended up being almost 64,000 water meters that we did. I put together a team of 8 different survey companies. 2 of us was going to do the GIS. Myself, my team, Wolper was going to be our partner in that, but they were also doing survey and Sioux. Had these 8 other firms. I had 3 firms that were going to do mobile LiDAR across the entire city, over 700 miles of roadway. And the different survey companies, Sioux companies that were doing the work. And the meters, I had 4 different firms doing meters. I had to plan out this whole thing so methodically. It took me over 2 months just to plan out what it was going to cost, how long it was going to take, because this was under a consent order with DEP. Now, the reason it was under a consent order because back in 2019, there was a FP&L subcontractor drilling underneath Fort Lauderdale Executive Airport, and they ended up drilling dead center on a 48-inch raw water line. Now, what happened after that was for 3 days, the city was basically shut down. So there was a lot of lawsuits and things like that. But anyways, on the 3rd day, they were still trying to find the valve. When they found the valve, it hadn't been exercised in 20 years. They couldn't, you couldn't close the valve. That's another problem. And then, so the contractor's boss came back into town. He went out to the job site, saw the situation. We happened to be out there with one of our crews and witnessed this. Contractor said, looked around the site, told his crew, go cut down that tree and use the tree and a backhoe to shove it into the water main, and it stopped. And there was pictures in the paper of that. So that's what started all this, why the city became under a consent order. Preliminary process, I mean, I had to look at things like the time at the asset, to collect the asset, the time between the assets, whether or not the asset was going to require MOT services. I went through this back and forth, how much time to add each asset. So you can see I went through this whole period, how long it's going to take. How long it's going to take with 2 crews, 4 crews, 6 crews. I needed to figure out how many crews I needed to do the work. We ended up narrowing down that process. We agreed. We actually cut out a lot of information from the scope. Started off with a $15 million project, ended up being $8.5 million that they agreed to. We finished the job in 18 months. We had 24 months to do it. We did it for $2 million under budget after we did that. Anyways, we had a tile scheme. This is tiles for aerials and the LiDAR for the city. We did the same thing, situation. We did a statistical analysis of the data to prove it. We ended up with this one being plus or minus 1800s across the entire city with this new LiDAR. It's very dense LiDAR set. We had the area cut into 3 areas for the mobile teams, so they wouldn't crisscross. They had to overlap 500 feet into each zone when they crossed it. We had multiple surveys across the city. Once I got the LiDAR, I had to overlay the LiDAR, check it against surveys we had done to prove the horizontal accuracy. The vertical, because they did the whole LiDAR data set. In order to get this done quickly, we told them to do it asset management LiDAR. So that means that they're only using the GPS unit they're not tying it to survey control. Every mobile LiDAR person that we tacked into told me they could do it and then provide half a foot accuracy across the whole city, horizontal and vertical, as long as there wasn't any tall buildings. So we had tall buildings in the downtown area, so we had to look at that. This is me looking at when they had more than 3 lanes. I had them drive 2 different directions on the road just to make sure I could prove out what they were doing. This is looking at the 2 different lanes, 2 different directions of the LiDAR. Most cases it was in this 2/10 tolerance, which was fine because I was looking for a half a foot. This shows the areas we cut the map up in. On the left there, you see 8 areas for the suit companies. On the right, you have the 3 areas for the mobile LiDAR people. And this is the areas for the meters. Using the meters. Here's the situation with the meters was they didn't have locations on them. All they had was an address. So I had to geolocate the meters using Esri. And of course, I geolocated based on the address. So what does that do? That puts the meter dead center of the parcel. Not the location, but dead center. How am I going to locate the meter? And some of the parcels had 2 meters on them, an irrigation meter and a normal meter. So I got with the city's water meter people, and they told me they had this little map on the side there. This is how they identify where the meter is on the individual site. So you have the house address. Address is based on the street that the address is to, and they have locations. Like so in their data sets on their mobile devices, they would say the meter is in position 1, 2, 3 on a particular lot. So the survey companies had to actually walk the streets, look at the database, where's the meter at? So they had to look in those positions, and it worked 99% of the time. There was several meters we couldn't find. The other thing we had to do was I had to, because I'm a GIS guy and most of those subs were not, except for one, I had to convert the GIS that I had into AutoCAD and Google Earth for them. So I had to come up with a way to do that so that they could identify the information in the CAD, send it to their crews to go out there and do the work. Because we weren't changing anything in the database. We were just moving it to the correct position. So we did not eliminate. We either broke the line, put a fitting on it, or we moved the line to its correct position, the valve to its correct position. So in AutoCAD, I came up with ways so I could identify, they could tell me that's a 6-inch border band. I don't care what the material was. So I came up with layers and symbols for them, gave them all the data in this format. That was another thinking out of the box. How can we get them to do GIS work without doing the GIS? So I also ended up giving them, because their crews were out there lost in the field, so I ended up creating Google Earth files of the GIS for them as well, so that their crews could look at it in Google Earth click on a feature in Google Earth and then get the data in Google Earth. And we had to come up with agreements with the city on things we found out in the field. So I found out that any pipes that was 24 inches or larger had butterfly valves. So the valve was tilted on its side. So the valve box was not over the pipe. I had to come up with ways of moving the fitting in the GIS to properly, and the valve had to be associated with the pipe ID so that we know how it was directly associated with that. So the city would agree with it. The hydrant assemblies were not included because they wouldn't be needed for the modeling purposes. So we had floating valves and hydrants out there. So telling the GIS people what to do, and the my GIS people and Wolpert's coming up with reasons why. Had situations where the GIS showed a bends in the pipe. The Sioux company comes back, there's no bends in the pipe. What we ended up finding out was situations like this, the GIS people, because they were producing maps in PDF format, some of the bends were actually vertical bends. So this is the way we handle that. We just move the fitting up to the pipe itself so that, and then based on the as-built, we could tell there was a vertical bend. Put that into the database. The opposite situation, we come on a pipe, they don't show any bend, we're showing a bend down the field from the Sioux. Add the fittings, put the information in. Google Earth is your friend in GIS and infrastructure. Google Earth Street View, Google Maps especially. Google Maps gives you the ability to go back in time. So you can look at a street today, they have the newest in there, but up at the top, when you go into Street View in Google Maps, it gives you the ability to look at different dates on the same thing. I used this extensively during this project to find valves that were hidden or covered, so that I could send the Sioux crew back out there, said the valve's there, this is about where it is, here it shows it. I made images like this. We used the parcel database from the property appraiser in order to get the right-of-way lines in, because some of the areas were not done by sewer, they were done by as-built. So I was able to use the as-built to determine how far off the right-of-way line the as-built showed it to be. We were able to place the mains where the as-built showed it based on the parcel database where the right-of-way lines were. And constantly I was being told by the Sioux companies, we can't find these valves. Can't find these valves. So this shows you what Google Maps can do. I looked at this one position, they said the valves were not there or they were covered up. This is a recent view. I could see the valves underneath this car, or some of them. Look back in time, you can see them all. So I would send them back out with this information to collect the data. So you can use that to your advantage anytime you get a surveyor out there that says they can't find the data. Of course, the as-built, some of the as-built were good, some of them were bad. We ended up producing, they had map atlases of each section, township, and range. So each section was its own map atlas. So they had no way of knowing whether or not the lines that were showing their map atlas were actually had an as-built for. So we had 2,500 as-builts that we had to go through on this. A lot of them were not as-built. They were actually planned engineering plans showing where it was supposed to be, but not necessarily where it is. So we would do things like this with the as-built highlighted, because we were only looking for water mains. We weren't looking for the other features in there. We would do this, and then we would take their entire map atlas sheet and show this as-built only goes along these lines. So now they have at least a system where they can look at the information we gave them to say, we don't have any as-builts in this, so we need to get them. These as-builts don't even reflect the as-built information. Of course, there was areas without as-builts. The lines were there, but we couldn't, so I had to tax them to go search for them. So the city we had a pretty good relationship with the city. They liked our work from before. They liked what we were doing. I was right on top of everything during this project. So they worked with me. This is what the atlas sheets looked like after we got done, showing them the extent of the different as-built and the areas that didn't have as-built. So this is the way we won the job. I went through these steps with the people for the presentation. Step one was the LiDAR acquisition immediately. Mobile LiDAR immediately during the first 3 months of the project, so we get the data. Aerial LiDAR and aerial photogrammetry. And I showed the city how we would use the data to collect information. You can see the valves inside the mobile LiDAR. Collect the information. The meters showed up in the mobile LiDAR. Different suit companies, what they were going to utilize, what worked and what didn't work. We had companies there that had this fancy Raptor system that you tow behind it. One of the other teams was claiming that they could do the whole city with it. I got with the manufacturer when I found out about it. I talked to them. I talked to people around the country that use the system. What I found out is you got a high water table, this doesn't work. Okay? None of these fancy systems work. So I was able to prove it that they couldn't use it for that. They could use it anywhere west of 95 in Fort Lauderdale, but not east of 95. Then I started doing an analysis of the database. They have abandoned valves that are still being shown. They weren't interested in, but I said we had to collect them because we didn't know that was an abandoned valve. So these were things that came up during that. I had to look at the existing database and analyze it before we actually did the job. This is my process before we got the job. I got a copy of the database. I looked at it. I saw that there was valves that had coordinates on them. They said GPS coordinates. So I was able to figure out that inside the database, because their maps were produced in PDF form for the field. They weren't looking at accuracy. They had an exact coordinate of the valve in some cases, but there was another notes, GIS notes in the database that said slid. So they were sliding the valves along the main to make it appear better in the PDFs. So I analyzed that, showed that we could save some time by not relocating these valves. And then the aerials. I needed high resolution aerials because the property appraiser had 1/2 foot pixel resolution. I needed 3 inches or better so that we could clearly see the different features, so we could utilize that in some cases just to move the features to their proper position. Back to the density of the aerial of the LiDAR and why we went to this. The reason why is because some of the features were not necessarily along the roadways when the mobile would pick it up. So you're thinking something simple as a fire hydrant. In mobile, you can see it clearly. But with 150 points per square meter, this is what you get. But you can actually pick it. So here's something you should think about if you're going to do this type of project in the future. So we ended up getting their deliverables was AutoCAD Civil 3D maps, Excel points of all point features, file geodatabase of each zone, mobile LiDAR data, aerial LiDAR data, aerial photography, zone maps, reports, and certified accuracies. So I just had a meeting with them yesterday. FDEP signed off on the consent order, so they're free and clear. And now they're looking to utilize that $2 million that's left for us to do additional work. Any questions? Hopefully I didn't tax you guys too much. Oh,
With the Fort Lauderdale Water System project, do you deliver a geometric network for that
No.
system? It was just that.
no, we were not, because one of the issues DEP wanted was they wanted the flows, which if you think of a water system, those flows could go different directions. So we talked with the engineers there. we discussed this, creating a geometric network, because I had done that for a city in North Miami Beach. And they said they need to look at it for modeling purposes. They're going to do that in-house. Yes.
The topographic LiDAR, is it still pretty limited? I know that there's some applications that use it for focus stuff. Is it pretty limited for the use for your application?
This is the issue with topography LiDAR. It's great as long as the water is clear. Right? If it has anything in the water, like, whether it's cloudy or whether I use it all the time. I do survey work for DEP down in the Keys. I can actually use a topography LiDAR, which was done in 2018, 2019, and it's going to be updated. Because one great thing about NOAA is they refly the coast after every hurricane. So you may not get the data for a year or so, but that data is coming. And I found that places like where there's water still, like the Keys, it actually penetrates and you can get a clear view of everything in. Now, I've used it in Hallandale Beach when they first started producing topographic LiDAR. Hallandale Beach Bridge, I think they call it Government Cut right there. They did it in that area. We were tasked to do a directional drill underneath the bridge there. The current that flows through there is like 15 knots. So trying to keep a boat still and get echo finders to get the data was very difficult. Anyways, we did it. We did like 4 or 5 shots. Took us almost half a day just to do it because of the current. The topographic LiDAR we used, we checked it against that. It was within a half a foot of what we got. For directional drilling, it was perfect. And that penetrated, I think the depth of the water there was 25 feet. So if you look at the coastline, which is what they do, they try to do it on calm days. And when they do it, if it's calm, the water is somewhat clear. So they do get down to, I think it's 15 meters they can get to. But just you have to remember though, it's getting when it hits the water, it refracts. So, so that data, it has to go through another algorithm in order to get the actual depth. So you gotta check the depths. But it is good data, especially in places like the Keys. I use it to identify mean high water. So I get the information from DEP, I take the LiDAR data, and I separate the LiDAR by 1/100th of a foot. I can classify what's above mean high water, what's below it, and I get a clear line of the mean high water. So something to think about. Another out of the box thinking. Yes. Anybody else? Anybody online? Questions? Yes.
You had mentioned briefly that you utilize LiDAR to find ancient remains and such like that. What process do you use when you're developing over those areas, particularly if you happen to have access to historical records?
I didn't say I did. I said they use it. I'm just showing you in that example. I showed you this is what reason why they can do that. I had a landscape architect at probably the late 80s when I started using GIS. And he came up to me one day and he goes, you know how in GIS and AutoCAD they have layers, you can turn them on and off? He says, can you turn off the trees? I said, not yet. So now you can. But the process I use 3 different softwares for LiDAR. I use Leica's Cyclone software. I use Google Global Mapper, which is a great software. It's fairly cheap. For $1,500, you can have a GIS LiDAR processor that's really good. I've been using that since they came out with it. And then I've also bought Quick Terrain Monitor. Quick Terrain Monitor is done by Johns Hopkins University. Put that out. I know a lot of LiDAR people that have gone to that. I think it's about $3,500 for the software. but it's fantastic stuff. Now, one of the things I want to caution you all on is coordinate systems. Now, I was involved with NGS, I think it's almost 3 years ago now. 2018, 2019, when they were looking at putting new state plane coordinates. They gave the opportunity to different states to come up with their own coordinates, correcting or just hold the same zones that they have. I took it upon myself, and then I had 2 other people help me. We ended up creating the new coordinate zones that you're going to see that are going to be 2026 is when they're coming out. So we have 3 zones. We're going to have 5 total zones in Florida. The 3 zones are going to be, the peninsula is going to be cut almost in half into 2 zones, the east and west zone. Then we're going to have the north zone, or the east zone, the central zone, and the west zone. Okay, the panhandle. What we ended up doing was looking at eliminating the as much of the error that we have in the state plane coordinate zones now. We're getting that down to, I don't have the slides that remind me of that. Anyways, by splitting it in half and extending the zones all the way up to the Georgia line, we ended up with less than half of the density, half of the error that we have now in state plane coordinates. Now, second of all, because I looked at not only DOT's work zones, but I also looked at the water management zones. We got by doing the peninsula, we did a separate zone of just the peninsula area going all the way up to the state of Florida, combining the east and central zones. By doing that, all of the water management districts in that area can use the same coordinate system. Where now the coordinate system overlapped. They had a problem with doing that. And because of the GIS people, now they are going to have a statewide zone. So that's the 5th zone it's going to be. So you're aware of it. And I'm sure the software companies will handle most of it. But it's a big issue. It's going to be a really big issue. The vertical datum is going to change. So from NAVD 88 to National Geo 22 datum, instead of 88, that's going to shift. It actually shifts in Florida from down the Keys as be within a 2/10. Central part of the state will be almost 0. North part of the state will be 2/10 the other direction. It's a little tilt. Basically, what they did was they changed the center of the mass of Earth, and that mass changed about 6 meters. So it's going to be, and we're going to have one North American fixed plate data across the United States. So look for that in the future. Any other questions? Great, thank you.
Thank you very much. So we're going to go ahead and take a 15-minute break.